gosh, I'm so glad you're here. I love radicals. I would say they're radical. We're going to review some properties of exponents, some properties of radicals, and this will lead us nicely into 5-6, where we have these rational exponents, which you'll get a little bit of a preview of today. So, perfect squares are what we're looking for. These are the super important numbers. 1 is 1 times 1. 4 is 2 times 2. 9 is 3 times 3. So these are all perfect squares, things you can square root, and it comes out to a nice whole number. They go on forever, but honestly, if you have them memorized up to 100, then you're probably good. And we're really going to ignore 1 because 1 is in everything, so we can kind of ignore that. Think of 4, 9, 16, 25, 36, 49, 64. 81, I forgot where I was, and then 100. If you can remember those, you're all good. So you can see the properties here, but don't worry about those. So we're going to break up 300 into perfect squares. So we have to think of a perfect square that goes into 300. So the largest perfect square that goes into that is 100. So I like to put all my perfect stuff, like you, in the left radical. So I'd put the 100 here, and it's 100 times 3. So you take the square root of the perfect squares, the square root of 100 is 10, and then you just mush it up with the root 3. 10 times the square root of 3, you would say 10 root 3. Another way, if you didn't know that 100 went in there, but you're like, okay, I know that 25 goes in there, you can say that that's 25 times 12. The square root of 25 is 5, so we'd have 5 root 12, but oh me, oh my, 12 still has a perfect square in it. So 12 is 4 times 3. Right? These things are all next to each other, which means they're all being multiplied. So when we take the square root of 4, which is 2, we're going to be multiplying it by the 5 that was already out there. This would also give us 10 root 3. Same thing we got over here, but you'll see we did less work. If you can find the largest perfect square, you just end up doing less work. So 8, a perfect square in 8 is 4. It's 4 times 2. The square root of 4 is 2, so you end up with 2 root 2. Ooh! 13 doesn't have any perfect squares in it, so you just leave it root 13. Not the most exciting thing, but hey, that happens from time to time, all right? 252. I have no idea what is in 252. So a lot of times when I'm doing problems where I don't recognize the number, I'll try dividing it by 2 or 3. Even if those aren't perfect squares, it might be a number that's more familiar to you. Or another thing I like trying is 252 is even, so usually I'll try 4. So let's see, 252, I'm not super familiar with this calculator. 252 divided by 4. Syntax error. Oh boy. I'm breaking everything. 252 divided by 4, 63. Okay, so let's use that. Even though I know that 63 has some perfect squares in it too, it's a starting place. If I can write. Okay, well, let's see here. What is going on? Okay, square root of 4 times the square root of 63. The square root of 4 is 2. What is happening? It's a Friday afternoon. Square root of 4 is 2. Now 63 has more perfect squares in it. It's 9 times 7. I'm just saving myself a line of writing here. Instead of writing 2 root 63 and then breaking down the 63, the square root of 9 is 3. So 2 times 3 give us 6. So this would be 6 root 7. Which means that originally 36 went in there, and it's 36 times 7, which if you can recognize that, which I didn't, then you can go straight to 6 root 7 a little bit quicker. Now if you look at number 5, 36 is a perfect square. The square root of 36 is 6. Now you might be wondering, oh, isn't it 6 and negative 6? Yeah, but when you're just simplifying radicals like this, you just take the positive answer out. Now, if you're solving equations with it, and you're taking the square root of 36, that's where you would use 6 and negative 6. All right, root 24 over 4. Now, the radical is only over the 24, so let's think of perfect squares in 24. That would be 4. So let's see. Everything's a little delayed. There we go. So 24, I'm going to make root 6, or root 4 times root 6. The square root of 4 is 2, so this would give us 2 root 6 over 4. After you take all the perfect squares out of the radical, you have to see if you can simplify any of the regular numbers that are left, not inside the radical. So like 2 and 4. By the way, I know I said take out all the perfect squares, and I know that 1 still goes into 6. Again, ignore the 1. So 2 goes into 4 2 times. It's like 1/2. So we'd have 1 root 6, or root 6 over 2. You're allowed to have radicals in the numerator. You cannot have them in the denominator. What if there is one in the denominator? We'll see on number 8. Number 7, root 27 over 3. 27, 9 goes into 27, and 9 is a perfect square. That's 9 times 3 over 3. The square root of 9 is 3, so we have 3 root 3 over 3. There are no more perfect squares in 3, so we check our normal numbers. 3 over 3 is 1. So we just end up with 1 root 3, or root 3. If you have a square root over everything, it is the exact same thing if you have the square root over each part of that fraction. And vice versa, if they give you the square root of 5 over the square root of 3, and you want to mush it into one square root, you can do that too. So, but again, you can have radicals up top on a fraction. You can't have them in the denominator. There's an easy fix, just like when we were adding and subtracting rational expressions. You can do whatever you want to a fraction, as long as you multiply the numerator and denominator by the same thing. So we are going to turn it into a perfect square. The easiest way you can do that is just multiply it by itself. So we're going to multiply it by root 3. If we do that on the bottom, we got to do it up top. So that would give us root 15 over root 9. And the square root of 9 is 3. So we end up with root 15, which has no perfect squares, over 3. Okay. You can save yourself this line of writing right here, that root 9. If you have the square root of 3 times the square root of 3, it ended up being 3. So if you have the square root of 11 times the square root of 11, it's just going to come out to regular 11. Or the square root of a times the square root of a would just be regular a. Okay, so that's something you can always keep in the back of your mind. All right, last one, root 12 over 5. Root 12 would be root 4 times root 3. The square root of 4 is 2, so we have 2 root 3 over 5. No more perfect squares in 3. Can you simplify 2/5 at all? No. So this would be your final answer. Now we're going to bring in some exponents that, they might have some fractions on them, but the same properties. Exponent properties, when you multiply and you have the same base, remember you add the exponents. So here, the base is 3. Did you hear my voice crack there? I was going to play it off like I did it on purpose, but nobody's perfect. Both have a base of 3, so we're going to add the exponents. So we're doing 1/2 plus 3/2. Now, if we do 1 over 2 plus 3 over 2, that would be 4 over 2. And 4 over 2 is just 2, so we're left with 3 to the second power, and 3 to the second power equals 9. That wasn't too bad, right? The second property is when you raise a power to a power, you multiply the exponents. So here we're going to be doing 3 over 2 times 2, which is 2 over 1, right? So if we clean that up a little bit, you could cancel out a 2 for a 2, which gives you 4 to the 3 over first power. 3 over 1 is just 3. So that's what that simplifies to. And then 4 to the third, 4 times 4 times 4 is 64. when you have multiple things in the parentheses, and you're raising multiple things to that power, then you just multiply all those things by that exponent. Now, this one's a little goofy. You could multiply the exponent on the 9 times 1/2, and that would give you 9 to the 1/2 power. And 2 times 1/2 is 1, so you have 9 to the 1/2 power times x to the first. And here's the thing, when you have these fractional exponents, whatever the denominator is, these are going to turn into radicals. Whatever the denominator is would go here. So we're looking for the square root of 9, and whatever the numerator goes here. So we're looking for the square root of 9 to the first. What's the square root of 9? 3. So it becomes 3 times the x to the first. 3 times x is 3x. That is one very obnoxious way that you can simplify that. The way they probably intended was like, oh, well, 9 could be written as 3 to the second times x to the second. And then when you multiply those exponents by 1/2, half of 2 is 1, so it would be 3 to the first, x to the first, which you would just write that as 3x. Other way, again, if you have a fractional exponent like this 1/2, then you take whatever the denominator is, you put it here, you take whatever the numerator is, the 1, and you either put it inside or you can put it on the outside. Usually I put it on the outside. So this would be really the square root of 9 times x squared, or 9x squared. And then after you take the square root, you take it to the first power, aka it doesn't change. So anytime you're having something to the 1/2 power, it's the same as taking the square root. And the square root of 9x squared is 3x. There's 3 different ways that you can solve that same problem. But where we're going in 5-6 is more of this pattern. Denominator goes there, the numerator goes right there. Okay? When you have a negative exponent, the way you make it positive is you put it on the other side of the fraction. So, if we are doing 25 to the negative 1/2 power, to make it positive, which you can't have negative exponents in your final answer. So you make it 1 over 25 to the 1/2 power. Now, like I just said, when you have to the 1/2 power, that's the same as the square root. So this is really 1 over the square root of 25. And the square root of 25 is 5. So this comes out to 1 over 5. You'll get used to the order of those fractional exponents. That's what we do in 5-6. That's what we do. All right. When you divide and you have the same base, you subtract the exponents. We just talked about this the last week. So here, these both have a base of 6, so we're going to subtract the exponents. So we are writing 6. There we go. 5/2 minus 1/2. Okay, those have the same denominator. Sweet. 5 over 2 minus 1 over 2 would be 4 over 2. And 4 over 2 is just 2. So we have 6 to the second power, and 6 squared is 36. We have one more property. Oh, it's a combination of raising a fraction to the power. You give it to everything. So you could say it's 8 to the 1/3 power and 27 to the 1/3 power. But let's think about those fractional exponents again. The denominator is the number that goes here. The numerator, or 1 in this case, would go here. So we're taking the cube root of this fraction. Now, luckily, both of those are perfect cubes. The cube root of 8 is 2. The cube root of 27 is 3. And 2/3 to the first power is just 2/3. So anytime something is to the 1/2 power, it's the square root. Anything to the 1/3 power is the cube root. Any guesses if it's to the 1/4 power? That's right, a fourth root. And that's why we pay you the big bucks. Way to go.